Okay. All right, what we're gonna do is we're gonna review. Just think of it as another lecture. You have a question. How do you know the differences with all these sines and cosines, and how does it work? Well, first, set this up. When really what it should be, what we should be more interested in is the inclined plane and the object here. Now, in the inclined plane, I typically give theta as that angle right there. In fact, it's horrible. Let me write it better. It's going to be the same drawing. You don't have to rewrite it, but I am. That angle theta. So this mass here has a velocity down the hill. Now I put the velocity arrow or vector not touching the mass because the mass itself is going to be the part that we call the force diagram. The main culprit of the forces is gravity. And that's the force of gravity, which is mg. We need to set up our reference system so that if you were to look at the mass in its reference frame, the x and the y would appear to be the normal horizontal and vertical. What we have to do is break the force of gravity down into its y component and x component. Now, there's a whole bunch of geometry reasons. There's an actual proof for this, but we're not going to be interested in the proof. But what I'm going to tell you is that that angle there numerically is the same angle right there. So those two have the same value. And if those two have the same value, then this could be shown as mg sine theta, and then this is mg cos theta. And so that determines the cosine and sine. Yes?
It's always going to be the top one and never the bottom?
What do you mean the top one and never the bottom? Point to the, what you mean by top?
This instead of this.
Correct. In fact, what that angle is, and I'll call it phi. Angle phi is 180 minus theta. So you have to keep track of that. But the way that this inclined plane is set up, those are identical angles always. And so we can effectively say for test purposes, if there is an inclined plane, that those are the angles. Yes? Excellent. Well, I think initially it's because you're I'm going to say this facetiously, so don't get this the wrong way. You're a victim. You're a victim of your trig teacher. And I'll show you why. When you have, pretty much for all of trig, you're shown this right triangle with that theta, that y, x hypotenuse. And what do they tell you? They tell you that sine of theta is y over hypotenuse, and cosine theta is x over hypotenuse. And they teach you that this is truth. But it's not. It can be. But if I said, well, I want to talk about the red theta, sine of the red theta is not equal to y over h. It's just not. Because the true definition of sine is the length of the opposite side divided by the hypotenuse, and the length of the adjacent side divided by the hypotenuse is the true definition of cosine and sine. It depends on the situation. But what they tend to do with you in high school is just say, sine of theta is y over h, and that's it. So very parrot-like. And hence the cycle of abuse is continued, because students who never hear it from me grow up, end up becoming trig teachers, and then repeat the abuse. So in this original picture, cosine theta is the adjacent side, FGY, over the hypotenuse, FG. Rearranging it, you get mg cos theta. You could do the same thing for FGX, mg sine theta.
How rearranging it do you get that?
Well, if you take cosine theta is FGY over FG, then that multiply both sides by FG. FG cos theta is FGY. FG is mg, so it's just mg cosine theta. And that's how you get it. So that helps set up the origin of all these sines and cosines and stuff like that. All right. What we'll do now is I've posted on the website the spring of 2016's test. And what we're going to do is we're going to do one of the versions. And if I'll tell you what version it is, this particular version, test 1, February 25th. The version, let's see if I can track down what this is. What I think we typically did was, it's the version where the conversion is 10. That particular number with the versions are different. So for this particular version of the spring test, look at the one, probably the first one, where you have to convert 10 cubic meters per hour. On another test, it may be 12. On a third test, it may be 14. And just take a look at that. So this is what I will call the 10 test. Now, as you can see, basic trig identities, a few conversion factors, stuff like that. Say that I didn't give the number of feet in a mile. I would think that okay, fine, I can give you that. I won't give you how many inches in a foot. Not gonna do that. I'm not gonna tell you how many seconds in a minute. Things that, as a human, you should be able to know in the 5th grade. just give me something. So I've got some basic equations. They're general. This is the position equation. In ballistics, there is no A for the X, but there is an A for the Y. What you do with the equations is your business. The odometer in a car measures what? Distance. Displacement over time is what? Average velocity. If it was distance over time, it would be what? Average speed. So now, we've gotten a lot of these. The multiple choice, what ends up happening is, I've got a list of 50 multiple choice questions. I have a spreadsheet that randomly selects 25 and then randomly reorders the multiple choice selections. So a lot of these are multiple choice. The multiple choice that you get, probably 80% have already been written. The other 20%, I'll just kind of sketch out, proof, change a few things. But a lot of this stuff just is seen over and over again. Like this one. You throw a ball in the air, which is a valid acceleration vector for the ball at its highest point? It's C. Now, for the person who said A, where does A come from? I'm sorry, where does the little a come from? Comes from gravity. Comes from the gravity of the Earth. Does the gravity miraculously turn off as the ball is at the top of the curve? No. It's constantly -10 as the ball's going up, at the top, as the ball's going down. I don't promise to do this. This is just an aside. There was a test where we did a one-dimensional vertical motion problem under the influence of gravity. And like I said, how long is the thing going to be in flight? What's the maximum height? And the third question was, what's the acceleration of the object 10 meters off the ground? And one of the students sat there and read it and then just looked at me like, seriously? And I was like, yeah, seriously. What is the acceleration of the object 10 meters above the ground? Same as it is going up, down, at the top, everywhere in between. So it was to prove the point. What was really funny about that moment, there were people who tried to figure out the time when it was at 10 meters high and then try to figure out the acceleration of the object at 10 meters. It was amusing to no end. Acceleration in a ballistics, where it's only under the influence of gravity. Gravity is always vertical, gravity is always down, gravity always has a magnitude of 10. And that's it. And it never ever changes. So what ends up happening a lot of these times, this has been used multiple times. Figure 1, so this, which plot represents velocity if G represents position? So G is position, which one of these is velocity? It's D, plot D. Because it's slowing down. The slope of this line decreases until it finally reaches 0. So the only line that does this is this.
If it were H, would it be A?
Yes.
Okay.
Now, in a case like this, if that is position and that's velocity, that would be acceleration. If that was position, then that would be velocity, and then that would be acceleration. So understand the relationships. Remember the particular lecture where I made a fool of myself running across the stage?
Yeah.
That's the moment that I want you to pay attention to. Normal force is always blank to the surface. What is blank? Perpendicular. The definition of normal from a physics perspective is perpendicular. You are walking forwards and speeding up. Which is true? Now, obviously, the answer is not E. An incorrect answer had scrolled off the side, so I just threw it in there. And then I told the class, the answer is not E. You're walking forwards and speeding up. So is the acceleration vector pointing forwards, backwards? Velocity vector is backwards. Acceleration points downward. A. When you're speeding up, acceleration and velocity are in the same direction. When you're slowing down, they're in opposite directions. Up is to down, as resultant is to A, equilibrium. If A is the resultant and B is the equilibrant, A plus B equals what? 0. Using figure 2, which is this, which one is mg? 4. Now, there was an interesting story about 9. I had an individual who he said, I'm from like Saudi Arabia or something. I've never driven a car. What is a speedometer or odometer? And I was like, you should kind of know that. So a speedometer in the car measures what? Instantaneous speed. Average speed, no, it doesn't do that. Acceleration vector is in the opposite direction of the velocity vector. So acceleration and velocity are opposite. You will what? Slow down. Your velocity is -3 meters per second and does not change. Your acceleration is 0. Chad Kelly throws a football to Coach Freeze. Which of the following is a valid velocity vector when the ball is at its highest point? A. At the highest point, its velocity vector can only be in the horizontal. At its highest point, its vertical velocity is 0. So anything mentioning y is not allowed, and anything mentioning 90 degrees is not allowed. So it has to be A. If B is acceleration, which is position? We've talked about this. B is acceleration, which is position? H. We forgot this. Book rests on a table. You push down on the book. The normal force does what? It increases. You spin a ball. It makes 2 revolutions. How many degrees did it rotate? 720. Each rotation is 360. 360 times 2 is 720. Number 16. -3x hat minus 3y hat is a what quadrant vector? Third. Excellent. Convert 2 nanometers into meters. A. So to do that, you have 2 nanometers, 1 meter per 1 times 10 to the 9th nanometers, and then you get meters. 2 meters at 100 degrees is a what quadrant vector? Second. Distance is the absolute value of displacement. Which of the following is the largest? E, yes. That's 1.2 times 10 to the third. That's 1.2 times 10 to the fourth. The biggest is that. So B is velocity. If B is velocity, which one is position? If B is velocity, which one is position? A. With B as velocity, it has a constant position. So has a constant velocity. So the position just does a steady drift. Kilogram is a unit for mass. Symbol for coefficient of friction is E, mu. What are the units of coefficient of friction? Nothing, exactly. If E is acceleration, which one is velocity? D, yes. If E is acceleration, it has a negative slope, that has the negative slope, or it has a negative value, so you're looking for the one with the negative slope. A mass hangs on a string. Which quantity is zero? Normal force. The only way that you can have a normal force is if it's resting on another object. So that is the multiple choice for this one. I think we're getting a gist of what it is. I'm not going to do the other multiple choice versions, but it's really just the same thing kind of over and over again. All right, now we'll just go over the this. I have not written the 213 test. 213 test is the most boring test ever. To me, at least. Why? Because you've got to hit the basics. You've got to hit, you've got to do the conversion. I mean, yeah. You've got to do vector addition. You've got to do 2D motion. 1D motion is a little bit. 1D motion actually is in this problem. Because 1D motion, when you look at this, the number line is bent. So in reality, an Atwood's machine is a one-dimensional motion problem. So conversion, vector addition, 2D motion, 1D or Atwood's machine, that's all we got. It's all we're ever gonna get. Now, the differences are, I could ask instead of velocity or time, I could ask for angle, I could ask for distance, I could ask for the masses or coefficient of friction. This is why I teach in the alphabet soup method. If you understand how to do the problem with letters, then you're good for anything. I'm going to get the shirt where it says, and on the 8th day, the devil said, and let them do math only with letters. Let's crank this out. Appetizer. We're going to convert 10 cubic meters per hour to cubic inches per second. I think this is a lot. I think I copied the conversion from last spring to last summer. So 10 cubic meters per hour. I hit the time first. 1 hour, 60 minutes. 1 minute, 60 seconds. I don't have to cube it. Why? Because time isn't cubed. Oh my God, cubic time, that would just be freaky. The other thing is I have to convert a volume to a volume, cubic meters to cubic inches. These I do have to cube. 100 centimeters per meter cubed. 1 inch, 2.54 centimeters cubed. And now we've got it. The number one mistake is that people do not cube the numbers that are sitting inside the parentheses. So it's 10 times 100 cubed, 60 times 60 times 2.54 cubed, and then so I get 169.5 cubic inches per second. Now I would accept 170, I would accept 169.51. I don't find it necessary that you use scientific notation in this. If it's on the order of hundreds or even thousands, I think you could get away with just writing it out. Actually, I know you could get away with just writing it out. But if you wrote, let me see if I can get the light. Oh wait, I got it. See how that number is on the bottom? 169.5104003. That annoys me. Don't write it all out. The purpose of this is not to let me know that you could write out 15 digits in a row. The purpose of this is for you to understand how to do the tasks. All right. Next, vector addition. In vector addition, you're going to get, and I get this a lot, I honestly didn't think he was telling us the truth. I thought he was lying like all the other professors. Effectively, I'm not going to just Xerox this and just ship you the same test. I'll change a few things and make it a little bit more interesting. But in this vector addition problem, you're going to get an instant conversion vector. So you're going to have to be able to recognize that it's an instant conversion vector and boom, convert it from polar to component. And the other one is going to be kind of a general, semi-nice vector where the reference angle is going to be either 30, 45, or 60. Let's take a look at this. A is 4 meters at 180 degrees. That's an instant conversion vector. This should not require, if the angle is a multiple of 90 degrees, you should not use a calculator to figure this out. It would take too much time. That instantly converted is negative 4x hat plus 0y hat if you want to write that out. I'm not a big fan of units during the problem. I think it just slows me down. For B, it is 3 meters at 300 degrees. Draw it out for a second. So this is theta A, which is equal to 300. It is a fourth quadrant vector. Fourth quadrant vectors imply that the angle is between 270 and 360, that you're dealing with a positive x but a negative y. The reference angle for a fourth quadrant vector is 360 minus theta A. That's for a fourth quadrant vector. For first quadrant, the reference angle is the absolute, for second quadrant, the reference is 180 minus the absolute. And for third quadrant, the reference angle is absolute minus 180. So being able to change these when it's necessary is important. So with 300, 360 minus 300, your reference angle is 60 degrees. The way that I do things, and for the people who are watching on YouTube and stuff, when you're adding a vector, you never put a negative sign in your calculator, and you should never get a negative sign out of your calculator. But Dr. Eschenberg, no. What did I just say? Never. But what if, nope, never. The way that the reference system of vector addition is set up, you never put in a negative sign, you never get a negative sign out. You are in control of the situation. Don't let the calculator be in control of you. Draw the vector out. You draw x and y. That is the b vector. That is your reference angle, which is 60. And then this is your x and y components. And more importantly, they're not necessarily the components, they're the magnitudes of the components. X is b cosine theta r. Y is b sine theta r. To my friend, the student who was academically abused in high school, in this particular case, now x is associated with cosine, y is associated with sine. Why? Because the y is now the opposite side, and the x is now the adjacent side. In the way that I have set things up, you could say that I am intellectually abusing you, because in the reference system, the x is always associated with cosine and the y is always associated with sine. The way that I've set things up is when I go, you always move x and then y, x and then y, x and then y, x and then y. In all four cases, regardless of the quadrant, the y is always on the opposite side and the x is always on the adjacent side. If you want to do it with a different system, be my guest. But I've just told you, stay on this path, follow these instructions, and the velociraptors won't eat your face. You do what I tell you to do, everything will be fine. You don't do what I tell you to do, I can't promise your safety and the wholeness of your face. So, in this situation, b cosine theta r is 3 cosine 60. Speaking as your private tutor for just a second, Dr. Eschenberg just goes nuts with 30, 45, and 60. He loves those things. Why? Cosine 60 is always 1/2. So this is 1.5. B sine theta r is 3 sine 60. Now, you do have to memorize, it's actually square root of 3 over 2, but I've never memorized what that means. And I get 2.60, so I'm just going to write 2.6. Technically, it's 2.59807. Whoopee. It's close enough. Where do I get the 3 from? I give it to you. Because A is 4 meters at 180, B is 3 meters at 30, or at 300. So the value of, I mean, it's a good question. The value of B in terms of its magnitude is 3. So that's where the 3 comes from. It's the length of the B vector. Yes?
Do we have to get the reference angle, or can I just multiply 3 times cosine of 300?
What you do, some of these work out right. And by all means, you can do it. And if you know what you're doing, great. The problem comes from when things jump rails and you're not quite sure what goes on. As an example, if you were to take the inverse tangent of components and keep the negative signs in there. Positive 2 over positive 3 is 2/3. Negative 2 over negative 3 is 2/3. So the answer coming out of your calculator would likely be a first quadrant number. Negative 2. Yeah, and so yes, what you're doing is a valid way of doing the problem. The problem with the way that you're doing it is you've got to keep track of a lot more moving parts, and you're really putting your GPA in the hands of the calculator. What this is doing, it's a very brute force, very simple way of doing things. Can you do 300? Yes. Should you? Your teacher's telling you no. Don't go jump in the Velociraptor pit. And what are you proposing to do? Well, I'm not going to jump in it. I'm just going to tie a string across the Velociraptor pit. Well, okay, I'm just going to take a video and YouTube it later. So it is doable. I just don't recommend it. So now we have the vector A negative 4x hat plus 0y hat. B, the magnitudes are 1.5 x hat and 2.6 y hat. It's a fourth quadrant vector. This is where our logic is applied. Fourth quadrant vector, positive x, negative y. That's where our negative signs come from. The reference system is dependent upon the wisdom and knowledge of the student. It's not, it requires that the student participate in the solution of the problem. We've done part one, the 3 parts. Break them, add them, recombine. Middle part, add, very fast. Negative 4 plus 1.5 minus 2.5 x hat. 0 minus 2.6 minus 2.6 y hat. This is the resultant in component notation. In fact, if we're going to do this accurately, wrap it in parentheses, put the unit outside. Now it's really ready. Dropping a unit on this type of problem depends on the attitude of the grader. Probably like 2 points out of 15. Missing a sign, 2 points out of 15.
I thought this one was 5 points. Is this what
The conversion's 5. The vector addition's 15. Now recombine. C is square root of x squared plus y squared. Those are the magnitudes of the components of C. So 2.5 squared plus 2.6 squared, square root. Square root of 13.01. 3.61 meters. The theta reference, if we draw this out, it's a third quadrant vector. How do I know? Negative x and negative y. So you draw x, y, cross it, theta r. That length is 2.5. This length is 2.6. Inverse tan of y over x. Inverse tan of 2.6 over 2.5. (46.1 degrees). So the answer C equals 3.61 meters at 46.1 degrees. And so that would be the answer. Now, in terms of, I know you guys round. I've rounded. Personally, for me, if I was going to add the vector and get the truest answer, I wouldn't do it by hand. I would do it on a spreadsheet. Or I would use the app, which effectively uses a spreadsheet. So 3.6, 3.55, 3.65 acceptable distances. 75 meters? No. 3.6, really good. Yes?
Since it's in the third quadrant, would you add?
Oh, you know what? Thank you. I'm not done yet. I was so eager to move on to the next part. Why? So what is, now to make me look smart like I intentionally did this, work with me here. What is the 46.1? It's the reference angle. So if it's a third quadrant reference angle, what do I do to get the absolute? You add 180. So 46.1, add 180, 226.1 degrees, so that goes away, and it's 226.1. Professor was more interested blathering on about some stuff, just forgetting the big picture. So 226 degrees is acceptable, 224, 228 also. Yes?
So you're really, in these problems, just looking for the C answer?
Yes. I am not looking for equilibrium in this problem. In fact, I've graded problems like this, and what I do is, and this is advice, probably 80% of the class is not going to follow my advice. Listen to the people right now on YouTube. Box your answer. Box it. Let me tell you what my graders are up against. They're having to grade 380 tests, about 240 214 exam, or 240 214 exams, 140 213 exams. They're busy. What would you do to help them out big time? Box your answer. If I looked at this vector addition problem and I just looked at this and I've got a little card that gives me the answers, and you have 3.61 and I got 3.6, you got 226.1 and I got 227, I'm gonna be like, good enough, 15, move on. And it's only when, if you had 75 meters at 83 degrees, we look at that and go, what is going on? If you don't have anything, that's easy to grade, that's 0. If you got the right answer, that's easy to grade, that's 15. We love those types of answers, either you knowing nothing or you knowing everything. It's the muddy middle that really gunks the system up. And then if you give the wrong answer, then we got to sit there and try to figure out what you did. And that just makes us angry. Yes? It's a third quadrant because when I added these vectors up, this resultant here gave me a negative x and a negative y. First quadrant, double positive. Second quadrant, negative x, positive y. Third, double negative. Fourth, positive x, negative y.
How can I remember, like, if I'm supposed to add or subtract 180 when I get to the final reference? 'Cause over here,
Oh,
it says
okay.
Yeah.
So over here, I wrote the conversions for determining the reference angle based on quadrant.
Yeah.
So what you want is, I want the determine absolute based on quadrant. Well, all you got to do is rewrite these, but let's do this a little bit more. For quadrant 1, trivial. Absolute is still equal to reference. For second quadrant, that's the absolute, and absolute angle, that is your reference angle. So absolute is equal to 180 minus your reference angle. For third quadrant, that's your absolute, that's your reference. So absolute is equal to 180 plus theta r. That, for fourth quadrant, that is your reference. So absolute is 360 minus theta r. What I typically do is I just draw the circles and then you just look at it. And so that's how I determine absolutes and references. It's a vector addition, it's just gonna be a power vector add. The numbers aren't gonna look, I don't think I could work it out so that I end up with whole numbers. I have to spend a lot of time figuring it out. I barely got done with the 214 test today. So I've got to write your test and print it out in the span of 4 hours tomorrow. That's gonna be fun. And just as a word of advice, for those who have questions about homework and you got a 0 on it, we'll work on it, we'll figure it out, but asking me today or tomorrow or Friday when I'm grading is a bad time to ask. I'm perfectly happy discussing it anytime next week, probably the week after. As long as we've talked about it before the end of the semester, we could fix things. Because all I got to do, I know the guy who changes the grades on Blackboard. He and I are tight. We always agree. So just focus on this. Now, next question. The 2D motion problem. Flat surface. Personally, for me, when I see a flat surface 2D motion problem, I get all excited because it's just so easy. Now, one of the things that I will promise you, there will be no quadratic problem. There will be no problem where the quadratic solution equation is necessary. Some people have figured it out, but it's not required. So for something like this, 2D motion, I haven't even read it, and I just write x equals x naught plus v naught x t, and y equals y naught plus v naught y t plus 1/2 at squared. Boom. First thing you do. Well, why is there no a in the x position equation? There is no horizontal acceleration. Everything is vertical. For a problem like this, the first thing you want to do is identify your origin, launch point, the usual launch place, or the usual place for the origin. That means x naught and y naught are both 0. One of the reasons, yes. No, I would, probably what I'd end up doing is flipping a coin. It could be, it could not be. Or if the answer is will it be a flat surface or will it be an uneven surface? Answer, yes. I will say that, speaking in terms of, for a flat surface, I'm allowed to ask for time because y final is 0 as well. That allows me to go negative 1/2 at squared equals v naught y t. One of the t's cancels. This one is now minus 1/2 at equals V naught y. Now, there is zero chance for this thing to require a quadratic solution. If it's an uneven surface, if it looks like this, one of the things that, unless I get really cute and invest a lot of time in it, but for test 1 of 213, particularly test 1 of 213 in the spring, I'm never cute on this test. It is as I've said before, the test will be boring. You should love it. For something like this, I would give the time. And if I give the time, then there's no way that this thing could be a quadratic solution. It's the procedure that I want you to understand. Because it launches up and to the right, the V naught y is associated with sine theta. The x is associated with cosine theta. So this becomes minus 1/2 AT equals V naught cosine. That was a very cute sneeze. There was one person during a test tried to keep her from sneezing, so she clamped down on her nose, and then she sneezed anyway, and it sounded like an exploding elephant, which was way more disturbing than just a normal sneeze. X equals, it was such a delicate sneeze, that's what the thing was. V naught sine theta t. I had a student one time hiccup during a lecture. I'm at the board, she hiccups, and then I turn around and look at the class and it stops. And I go back to the board, she starts back up. And on the third time I turn around, I'm like looking around, and someone raises their hand and goes, "I'll tell you who it is for a couple bonus points." And I'm like, no. Such a try. Not really. Never. Almost. The philosophy, excellent question. The philosophy that I've developed is I used to give a 10-point bonus problem on a test. But what is the purpose of the bonus? Is to help the people out who aren't doing that well. Well, what happens is that the people who are going to get A's get the bonus anyway. The people who need the points can't do the bonus, and what it ends up is the nightmare scenario. I don't get a bell curve, I get a barbell curve. So you've got the haves and the have-nots. So what I've done is, instead of giving bonus, I curve viciously, always up, and it works out. I curve the tests. I'm here in a way to let you know what's on the test, but I'm doing a little bit of preventive maintenance therapy at this moment. Let's say the instance, the typical average on a test 1 is, for the spring, could be 65 to 75. Sounds bad. But what I do is I say minimum curve plus 2, reserved to increase at a later date. So, because what happens is, my nightmare scenario is realizing that the only way that I could fix the problem is by curving down, which would cause anarchy. So the best way for me to do it is to make the tests a little bit on the harder side, get that bell curve down, and then I can shift, and then that fixes the problem. I'd much rather have a test too hard than too easy. Now granted, from your perspective, why don't I just give everybody A's and then we just go home and leave me alone? Well, that's not how we play it. So, you gotta learn something, yes. You know, right, it is. I was distracted by your friend's questions. And then the sneeze threw me off guard and we all went downhill from there. V naught y, and you can see it, V naught y is the opposite side, So V naught y is V naught sine theta. So it's, thank you. Once again, I intentionally made a mistake to see if you guys were paying attention. Now looking at this, I don't think this will show up all that well. Red bars above are unknowns, green bars below are known quantities. I don't know V naught, and I don't know time. But I do know x 50 and theta 30. That equation has two unknowns. I can't really do much with it right now. Over here, I don't know time, I don't know V naught, but I know I'm on the planet Earth. A is -10, which effectively means it's -g. And I know what theta is, that's 30 degrees. This is a 2 equation, 2 unknown problem. You're gonna get one of these. Not specifically maybe associated with a different problem, but for this guy, it is a 2 equation, 2 unknown. How do you solve? Solve for one of the unknowns over here. Let's say t. Why not V naught? We could do either. Doesn't really matter. So x over V naught cosine theta is equal to t. Substitute that in. -1/2 a x over V naught cosine theta equals V naught sine theta. Now the only unknown in this case now is V naught. Solve for V naught. Minus ax over 2 cosine theta sine theta equals V naught squared. The V naught comes up and squares, the sine comes down and forms this, minus ax over 2. So the square root of minus ax over 2 cosine theta sine theta is equal to V naught. And that gives you V naught. Let's solve. -10 x 50, 2 cosine 30, sine 30. Once again, why do I like 30 degrees? Because sine of 30 degrees is 1/2. 2 times 1/2 is 1, they cancel. So this is -500, or I'm sorry, I take it back. Negative of a -10 gives you +10. So this is 500 divided by cosine 30, square root. And V naught is 24.03 meters per second. You could write 24, I'd be fine with that. 2 equation, 2 unknown. V naught has just become a known quantity. X is 50. V naught is 24.03 cosine of 30, and that is equal to time. And I get 2.4 seconds.
So you can solve for either unknown, like
Yeah.
you can solve for Tom initially.
Mhm. Yeah, the order of the solution is irrelevant. You'll get the same answer. Or should I say same answers? Okay. The last part, the Atwood's machine, has been part of, and actually, I'll tell you, the girl who's, the reason why Atwood's machine is on, yes. Okay. So while he's writing this down, I'll tell the story. I used to teach in here. I gave test 1 in here. There was a student probably 3 rows behind you, but more closer to the wall, calls me over and says, you told us that there wouldn't be an Atwood's machine problem on the test. I was like, did I just slip into an alternate reality where I may have said that? No, it's impossible. And not only did I say it was going to be on the test, you have now guaranteed it will always be on the test until the class gets it right, which means it will be on there until the sun dies, until the Andromeda Galaxy collides with our galaxy 4 billion years from now. Physics 213 test 1 will always have an Atwood's machine problem on it, as long as I'm alive. So there's stories behind these problems. Some professors just like randomly put stuff together. These mean things. Atwood's machine, initially known motion. What I'm looking for is, I'm looking for time and I'm looking for acceleration. Those are the power, straightforward values I'm always looking for. The graders will be informed to look for derivations. You will have to derive what A is. You cannot say, poof, a miracle occurs, and write the equation down for the very end. One of the things that I do in order to prevent that is, let's discuss it. When you do this problem, there are 2 masses experiencing tension. There's the hanging mass, and then the mass that is up on the edge. That string experiences the tension, or inflicts the tension on the objects. This object has a certain height above the surface, which is L. This is why I believe that Atwood's machine is a one-dimensional problem. You're gonna have in order to determine the time that it takes to go down there, you've got x equals x naught, which is 0, plus v naught t. V naught is 0, plus 1/2 at squared. X is the length, which is 20. A is the acceleration of the system that you determine. So 2x over a is equal to t squared, or the square root of 2x over a is equal to t. So I could give you the height and acceleration, you can get the time from that. Or I give you time and x, and you can get acceleration from that. There's several different ways that we can do this. Algebraic manipulation. According to the person who hated me the most and wrote the most vile, oh, it was deliciously evil, she hated me. And she basically said, Physics 213, all it is just applied algebra. Duh. Yes, it is effectively a continuation of the algebra and trig courses that you took in Hume. It's just a little bit more applied, with some ideas behind it. What you're going to do is you're going to sum up the forces along the axis of motion for each of these. You apply the loopy-droopy number line. To the left is negative, to the right is positive, and we bent it in 90 degrees. So right and down positive, up and left is negative. We've got to sum the forces here. Let's do this one first. M1 and M2. Let's do the second one first. You have no normal force, so you can sum the forces in the axis of motion as M2 over A. If there's motion in that plane, and you know there's going to be acceleration, the sum of the forces is equal to MA. Now, what are the forces? What are the, I know, the force. Tension is up, For this reference system, up is negative, down is positive. So negative tension, down is the force of gravity. And so what we get with a little rearranging, T equals M2G minus M2A. All I did was put the tension over here, the M2A over there. Why? Because we're gonna factor out tension. In the end, once again, the Atwood's machine is a two equation, two unknown, and we need to just dump it. Let's sum up the forces on the other one. Let's draw it a little bit bigger. You've got the force of gravity again, or M1G in this occasion. You've got normal force up, you've got the tension pulling to the right, and then you've got friction force pulling to the left. So that's the sum of the forces. You do the things that we've always done repeatedly. Sum the forces in Y, which is 0. There's no motion in the Y. Why? Because it's sitting there on the surface. Normal force up, positive. Downward force, M1G, negative. So the normal force is M1G. We want to see this derivation. Last fall, there was an external force wandering around, messing with the system. For this particular class in the spring, no, I'm not going to do another external force. It'll just be the straightforward stuff that we're doing right now. Step 2, friction force. Mu sub K M1G. Now it could be in a situation like this, the cuteness factor of the test is going to be at an all-time low. So what I may end up doing is, rather than simply asking for time and acceleration, go, give me the value for the friction force as well. And so what you would do is you would just take the numbers, plug them in. Mu sub K is 0.1, M1 is 1, G is 10, so this is 1 Newton for friction. Give me that number. And so that hasn't been done. And really, let's once again, I'm going to break into private tutor mode. Dr. Eschenberg has a weakness. Dr. Eschenberg's lazy. Dr. Eschenberg gets bothered by his students all day. So what does he do? He sits there and he writes the test during the review session. He just sits there and goes, I wonder if that works out. Let's just see. If the problem like that works really well, there's a higher probability it's going to get in the test. Let's say I do a problem and it just bombs and just trips over each other. Then I'm gunshot. Then I sit there and go, I don't want to do this. Not put it in the test because I made just an utter mockery of it the night before during the review session. So pay attention to these things. Am I going to do this part? Not sure, but it's now in my mind. So who knows? The third part, sum the forces in the axis of motion, which is M1A. Notice that I didn't make a difference between the A for mass 1 and the A for mass 2. Why? Because the accelerations are the same, just as the tensions are the same. And so that is it for the equation of motion for this. Rewriting it, M1A plus mu sub K M1G is equal to tension. I never really asked for the tension in the Atwood's machine. If I don't ask for it, you can eliminate it because the two unknowns in this situation are A and T, A and T, T and A. So what we do is I've solved for T for both, set them equal to each other because the tensions are the same. M2G minus M2A, M1A plus mu sub K, M1G. And then what we do is we solve for A. M2G minus mu sub K, M1G, M1A plus M2A. Factor out G's and A's. G, M2 minus mu sub K, M1, A, M1 plus M2. So A is G, M2 minus mu sub K, M1 divided by M1 plus M2. And that's the acceleration of the system. G is 10, M2 20, minus mu sub K, which is 0.1, M1 is 1, M1 1, M2 20, and so that's it. So 19.9 times 10 divided by 21. So 9.48 meters per second squared. It's a valid number. What? Yes?
So do you want us to show that whole process to get to the A equals?
Yep. Once again, do you expect me to show all the steps? Nice try. And now what you do is you take the t, put it in 2 times x, which in this case is 20, divided by 9.48. .05. Notice that when you get the value of A, it has to have both qualities. A has to be positive, B has to be between 0 and 10. If you get a negative number or you get a number greater than 10, then you've messed up somewhere. Yes?
So you need to explain again, so where you did, you sum the forces for mass 2, is that, why did, can you just go over where everything is?
Now, the sum of the forces on mass 2 in its plane of motion must add up to M2A. So what are the forces? The force on the mass pulling up the tension, and then the force pulling down because of gravity. Down in this case, because of the loopy droopy number line, is positive. T is up in this case, according to the loopy droopy number line, means it's negative. So that's why it's negative T plus M2G. Solve for T. I get that. And that's the setup for this. So, yes?
What if you decided to mean add a force to M1?
In this particular class in the spring for 213, I don't add the external force. Had you been here 15 minutes ago, Pav, you would have heard that. But you show up late, as always. Huh?
It's your last semester when we had it.
Yeah, they're not going to get it. They're not going to get it. And so that's it. And so just go over the multiple choice, go over the review session on Tuesday. I would probably spend most of my time efforting on lecture notes. I mean, if you're going to be efficient with your time, rewrite all your lecture notes and understand every single step that I've done in that. And if you can do all that, then you're effectively prepared for this test. That's why you show up to a review session, to get these pearls of wisdom. All right, we're done.